Hi everyone, my name is Ramkrishna from IIT Madras and welcome to this lecture series of week 6 on linear systems theory. So last lecture we had defined for ourselves few concepts of stability, starting with just the notion of a stable system where the solutions were uniformly bounded. Then you had the notion of asymptotic stability, which did not tell me about the rate of convergence of my solution to the equilibrium point. And then we had the exponential stability notion, which had some information on how fast my solution approaches the origin. And of course, unstable systems, the systems which are not stable are unstable systems. In many of these cases, we were talking of solutions converging to the equilibrium point, and in many cases it may be difficult to compute the solutions explicitly and check whether they are stable or asymptotically stable or not, right. Even though we have the beautiful notion of the state transition matrix and computations involving state transition matrix, which can give me the expression to the solution explicitly. Now, are there better ways of verifying this? Loosely speaking, can we find an analogous to the stability verification via the location of poles in when I look in terms of a transfer function representation of a system? Yes. So, that will be the focus of today's lecture, and we will also look at how to not only have conditions to verify stability, but how do we even prove some notions of stability. So to begin with, okay, let's start with a bit of math preliminaries, because we will be dealing a lot with matrices here, right. So I would like to define some notions of norm on matrices. So just for any m cross n matrix A, each element of A has this form Aij. The one norm is defined in this way. So I am looking at this could be the summation over the columns, and I am looking at the maximum column sum of the matrix. So in if n equal to 1, I realize the standard vector case. So I have a vector now instead of a matrix, and the one norm would simply be the summation of all the elements of A. So say I equal to 1 to m, like the standard definition of a one norm of a vector. Okay. Similarly, with the infinity norm, here I am looking at the maximum row sum. Okay. And similarly, I can derive that for n equal to 1 case, I will have a vector, and this definition will coincide with the definition of the infinity norm for in case of a vector. Okay. Next is the notion of a 2 norm. So the 2 norm is defined in the following way. The 2 norm of A is just the maximum singular value of this matrix A. And last notion is that of Frobenius norm, defined this way. Okay, we will not use much of this in this course, but just nice to know some definitions. Okay, so what are the properties of norms defined on vector space that will translate to norms on matrix? Well, one thing is obvious, that all norms are equivalent, like we proved in the vector space case. What does it mean by equivalence? That one of them can be upper and lower bounded by any others times a multiplicative constant. Say the one norm can be upper bounded and lower bounded by the infinity norm with some numbers alpha and beta here. Okay. Another important property is the submultiplicative property. Right. So, if I have two matrices A and B, the submultiplicative property says that the norm of A times B would be less than or equal to the norm of A norm and times the norm of P. P could be whatever, P could be the 1 norm, the 2 norm, the infinity norm and so on. Okay. So, from the definition of the submultiplicative norm or the property of submultiplicativity, we can define what is also in literature usually referred to as the induced norm. Okay. So, I will quickly run you through what this could mean. So, for any submultiplicative norm, so here A is a matrix, X is a vector. So, A times X, some P norm could be 1, 2 or infinity is less than or equal to the norm of A and norm of X for all X. This would imply that I can rewrite it this way, that A of P is greater than or equal to the maximum with the X not being equal to 0, the norm of A x divided by the norm of X. Okay. A slight little definition here would be or a property would be that these 1, 2 and infinity norms are subordinate to the corresponding vector norms. What does this mean? That we have A of P is actually equal to the maximum or also referred to as the supremum over all the X. So, I just check for all the X and find what the supremum of this ratio, right, A x P over P. Okay, this is a little typo here. Okay. So, where does this come? So, this equality arises from the fact that these norms have the property that for every matrix A, I'll write it properly, for every matrix A there exists a vector x star in R n for which A of P is A x star P x of P. And P could be 1, 2 and the infinity norms. Okay. So, if I just say, just take the case of a 1 norm, and this would be the maximum of over x not equal to 0 A x 1 over x of 1, right. So, this is what I would get when I just look at the 1 norm starting from the definition of an induced norm. Now, is this norm, which I call it 1, label it as 1, equal to the 1 norm that I defined here, right. So, if I go back, so the question is, okay, I will just write it over here, is 1 equal to 2? Okay. The answer is yes. It's a little proof, not very complicated. So, I will skip the proof, but you can just follow this link of another NPTEL lecture on numerical analysis. So, these notes will give you a very nice exposition to the proof of this. Similarly, you can replace the 1 by 2 here, just call this P to be 2, and you can prove that this will actually give you the 2 norm, and so on with the infinity norm also, right. So, there is a good equivalence between the definitions of the 1, the infinity and the 2 norm, and what I derive here via the submultiplicative property. Okay. So, of all these properties, this is what we will be using in this lecture. Now, a little to do with definitions or some properties of positive definite matrices. Okay, what is the definition? Just take an n cross n matrix Q is positive definite if x transpose Q x is greater than 0 for all x except the origin or except the 0 vector, right. Okay. Now, again, how do I test if the matrix is positive definite or not? Well, if I go by definitions, I may have to check all possible vectors which are in Rn and verify this condition that x transpose q x should be greater than 0. Okay. So, this x transpose q x will be in R, right? That can be checked or observed quite easily, right. But I would not want to do this for all x and take forever to check if a little, even a 2 cross 2 matrix is positive definite or not. Okay. So, before we look at what are the ways to define, what are the ways to check if a matrix is positive definite or not, I just list some properties that such matrices are always invertible, and this is also a good property, that also means that they are non-singular. Another good property is that the inverse of a positive definite matrix is always a positive definite matrix. Again, the proofs might be pretty simple, so I just skip. So, if I instead write x transpose q x less than 0 for all x in Rn, then this will define for me what I call as a negative definite matrix. And if instead of the strict greater than sign, if I just replace it by greater than or equal to, it will be called a positive definite, positive semi definite matrix, and with a less than or equal to, so in this case, so this will be a negative semi definite matrix. So, I am just talking of the properties of this Q matrix: positive definite, negative definite, positive semi definite, and negative semi definite. Now, how to check computationally if the given Q matrix, a square matrix, is it positive definite or not? Okay. I cannot compute all x transpose q x for all x in Rn, that will take me infinitely long time, but I will just see if there are alternative methods of doing that. So, that is what is in the next slide. So, q being positive definite is equal to saying that all eigenvalues of q are strictly positive, right. Okay, here I am also talking of symmetric matrices only, right. So, this should be stressed. Okay. For a symmetric n cross n matrix Q, whenever I say Q is positive definite, it also means that all eigenvalues of Q are strictly positive. Okay. Not only that, this is another way of testing is the determinant of all upper left submatrices of Q are positive. So, let us say I am just looking at a matrix of 3 cross 3. Okay. So, what does this mean? That okay, first A11 should be 0, and if I compute the determinant of the 2 cross 2 element starting from here, this determinant should also be positive. So, A11 should be greater than 0, the determinant of these 4 elements A11, A12, A21, A22 should be positive, and this also should be positive, the entire determinant of the matrix. So, these are all the upper left submatrices of Q, this one, and of course, the original one by itself. Okay. Is there another test? Well, yes, there exists. So, Q is positive definite if there exists an n cross n non-singular matrix H such that Q can be represented as H transpose times H. Okay. So, again this H should also be invertible. A final property which again I will not do the proof, but we will use this extensively, is that given a matrix Q, so X transpose Q x, right. So, which will be greater than 0 when it is a positive definite matrix, when Q is a positive definite matrix. So, this will be lower bounded by lambda min Q times the norm of x square and upper bounded by lambda max. So, this is the minimum eigenvalue, and this is the maximum eigenvalue. Q. Okay. This should again be easy to verify, and I will not do the proof of this. So this is what we will use in our stability proofs. Okay. Now another result that we will use later in the proofs is the following, and I will do this the proof of the comparison lemma in a supplementary lecture after I finish the main lectures in this week 6. So start with a differentiable function Vt be a differentiable signal for which I have some kind of a differential equation involving V, that V dot of t is less than or equal to mu times Vt. Well, for all times t greater than t is 0 and some mu being some scalar quantity. If this holds, it turns out that V of t is less than or equal to the signal, so e power mu t minus t 0 times V at t 0. It sounds intuitively it looks a little okay, but we will actually prove this later on. But this will be another result that we will use extensively in this lecture. Okay, now coming back to how do we check for stability. Again, the motivation is, can I have some better test than by just verifying solutions if they are stable, asymptotically stable, exponentially stable, and so on. So the definitions here would give me some tests based on the eigenvalues or the properties of the A matrix. Okay, so we start with the linear system. Again, this is LTI system, x dot equal to Ax. I do not explicitly consider the influence of B at the moment, but this is give us a nice exposition to what is coming up. So the system 1 is marginally stable if and only if, right. So it works both ways. All eigenvalues of A have negative or 0 real parts. So like very much to do with the poles. If the poles are here, the eigenvalues are here, here and here, this is all stable. Okay. And not only this, so this 0 real part comes with one more condition, that all Jordan blocks corresponding to the eigenvalues with 0 real parts are 1 cross 1. So what does this mean? So if I have poles of the form plus minus j, like repeated poles on the imaginary axis, this system shows out to be unstable. Okay, you can check for this condition. These are also in any earlier control lectures of basic undergrad control engineering would tell about this. Right? If there are repeated poles on the imaginary axis, then that leads to instability. Okay, how do the solutions look like? Say in this case, so these poles will have exponentially decaying term. So this will in some sense have some kind of an oscillatory behavior, essentially because of the poles on the imaginary axis. If there are no poles on the imaginary axis, you might actually find that the oscillations might just die down, right, depending on what kind of damping is exhibited in the system. Okay, so back to definitions of stability, or how do we verify with eigenvalues? Well, the eigenvalues should either be on the imaginary axis or to the left of it. The only caveat here is that if they are on the imaginary axis, I need to do an additional test corresponding to the Jordan block. Okay, asymptotically stable is easier. This is that I just have to check if all the eigenvalues should be on the left half plane, no eigenvalues on the imaginary axis. So the definition or the theorem says that the system is asymptotically stable if and only if all eigenvalues of A have strictly negative real parts. Similar thing holds also for the exponential stability case in the LTI case. So that is what we had claimed, not claimed last time, but we had I had mentioned to you that in the case of a linear time invariant system, asymptotic stability is also equal to exponential stability. It may not be true in other cases of nonlinear systems, but we are not interested in that, but we will slowly prove this in this lecture. Last thing about unstable system, well, the system is unstable if and only if well, if there is one eigenvalue on the right half plane, then it is unstable. Again, if there are imaginary eigenvalues or eigenvalues with 0 real parts, then the corresponding Jordan block should be of size larger than 1.1, for example, in this case, right. So, that is the only thing that we must be careful of. What we will prove is are not things related to instable or unstable systems. I will just prove conditions related to stability. So, let us first begin by showing that that for LTI systems, asymptotic stability is equal to exponential stability. Okay, so I start with again x dot is Ax with solutions of the form x of t is e power a t x 0, with x 0 being the initial condition. Okay. So, well, lot of it depends on e power a t, and what we know that if the eigenvalues of A have strictly negative real parts, right. So, the real part, okay, let us say the real part of the eigenvalues are strictly less than 0, then this would mean that all entries of e power a t converge to 0 exponentially fast. Right. So, as t goes to infinity, the entries converge exponentially fast, and therefore, e power a t converges to 0 also exponentially fast. Sorry. Okay. So, this could be for any matrix norm, 1 norm, 2 norm or the infinity norm, and therefore, this would mean that there exists constants c comma lambda greater than 0 such that e power a t is less than equal to c e power minus lambda t, again for all t. Okay. Now, how does the solution look like? X of t, the norm is e power t, let me assume t 0 to be equal to 0 just for simplicity, e power t times x naught. So, this will be less than or sorry e power a t, this will be less than or equal to again e power a t x naught. So, here I am using the submultiplicative property of matrix norms. Right, and now with this expression I know that this is c e power minus lambda t with x 0. Okay. So, what does this mean? That the solution, okay, now check what happens to x t as t goes to infinity. Okay. First thing I can obviously say that this converges to 0 as t goes to infinity, again assuming that all the eigenvalues of A are strictly less than 0, which means e power a t converges exponentially fast and so on. Okay. Now, how fast does this converge? So, even before I ask this question, so this is already tell me that the system is asymptotically stable. Okay, how fast does this converge? And I go to the right hand side and I see that the solutions can always be upper bounded by some exponential curve here, exponentially decaying function here, and therefore, this also leads to the equivalence between asymptotic stability and exponential stability for a linear time invariant system. These two are indeed the same concepts, right. So, again the steps are pretty neat to follow. So, what we showed here is the following, that that asymptotic stability would mean that all eigenvalues of A have strictly negative real parts. Not only that, whenever A has eigenvalues which are strictly negative in their real part, this also means that they are naturally exponentially stable, right. So, that is the little proof of the equivalence between asymptotic stability and exponential stability for LTI systems. All the time again, computing eigenvalues may be computationally difficult for me or computationally expensive, even though I am doing it on a computer, say via MATLAB for example. For a large size matrix, it might take me a very long time. Now, are there another or better kind of conditions that I can check which are maybe computationally efficient for me to verify if the stability, if the system is asymptotically stable or not. Now, I am interested in asymptotic stability, or I will just use one word, either asymptotically stable or exponentially stable, and they would mean the same. So, these are two nice looking conditions that in addition to those eigenvalue conditions, stability of the LTI system is also equivalent to saying the following, that give me any matrix Q, right, for every, right. So, for every symmetric positive definite matrix Q, stability would mean that there exists a unique solution P to this following Lyapunov equation, right. So, given Q, A is the system matrix, can I find a P? So, if a P exists, this and this, then the system, so the solution to this, if a solution exists to this equation, then the system is exponentially or asymptotically stable. Moreover, the P is such that it is symmetric and positive definite, right. So, we will prove this. Second condition says that there exists again a matrix P which is symmetric, positive definite, for which this inequality holds. Okay. I will give you a little gist of the proof and then we will go into the details of it. So, first we need to understand what is given to us and what is to be proven. So, the part 1 of the proof goes in the following way. So, we will check that when the system is exponentially stable, it actually implies this equation. Okay. So, we will begin by showing that the unique solution is given by this indefinite integral from 0 to infinity and blah blah blah. Okay. So, I know that the system is exponentially stable, right, that the system, the LTI system is exponentially stable. Okay. So, first I need to check the properties of this integral, that this integral actually converges, that this is actually finite. Okay. Second, I need to show that if the system is exponentially stable, which means e power a t converges exponentially fast and so on, that if this is true, then this P actually solves this equation. Okay. Not only that, we also should show these extra properties, that this P whenever it solves that equation is actually symmetric and positive definite. Lastly, we also should be able to show that this P is unique, because I am looking here at a unique solution P to the to this what I call as the Lyapunov equation. Okay. So, what does stability mean? Given a matrix Q, can I find P which solves this equation such that this P is unique, it is symmetric and positive definite. Okay, let's do these steps one by one. So, I have P 0 to infinity e power a transpose t q e power a t dt. Okay, first, is the integral well defined, or does this integral actually exist, that 0 to infinity of some function should not give me infinity. Okay. So, what do I know? I know that the system is exponentially stable, which also means that the eigenvalues of A are strictly less than 0. I am talking of the real parts of eigenvalues of A being strictly less than 0, and therefore, if I look at this quantity e power a transpose t q e power a t. Okay. So, this will converge to 0 exponentially fast as t goes to infinity, right, and therefore, I can say that this integral is absolutely convergent, or this limit actually exists, right. That is, so what am I making use of the property? I am making use of the property that A is an exponentially stable matrix, and that is what gives me. So, conversely, if A is unstable, then this would not go to 0, right, this quantity would possibly blow up and go to infinity as t goes to infinity, and in that case this integral is not well defined. Okay. So, this is the step number 1 is done. Okay. Step number 2, now does P solve this equation A transpose P plus P A is minus Q. Okay. So, A transpose P plus P A is, okay, just substitute this in this equation. So, I will substitute for P, get 0 to infinity A transpose. So, what is P? P is e power A transpose T Q e power A T plus P. So, P is again e power A transpose T Q e power A T times A dt. Okay. So, okay, closely look at this quantity inside the bracket. So, this is essentially d by dt of e power A transpose T Q e power A T. Okay. Okay. Now, what am I left with? So, if I replace with the d by dt, I have integral of 0 to infinity d over dt e power A transpose T Q e power A T dt. Okay. Now, this is okay. This is looks simple now, right. So, I have e power A transpose T Q e power A T with limits from 0 to infinity. Okay. So, this is what. So, the first one would be, so I am looking at the limit as t goes to infinity e power A transpose T Q e power A T minus, okay. So, when t equal to 0, this will be e power A transpose 0 Q e power A 0, when I am just looking in this, the second term as t equal to 0 and the first term as t goes to infinity. Okay. Now, look at this term carefully. What happens to this term as t goes to infinity? I know that A is a stable matrix, exponentially stable matrix. So, these entries will go to 0 as t goes to infinity. So, I am left with a 0 here minus. So, what is this? This is the identity, this is the identity. So, I am just left with a minus q. Okay. So, what I have shown here is that this p solves this equation, right. I substitute for p here and I get q, right. So, I know now that p, which I defined it in this way, actually solves my equation. Now, is that enough? Well, not really. Third step would be to check if P is P transpose and if P is positive definite. Okay. The first step should be easy to check. Start from here. What is P transpose? P transpose is 0 to infinity. I just have these 3 matrices and I just invoke the transpose formula. So, I think if I write it correctly, A B transpose is B transpose A transpose. Okay. So, this will be e power A transpose T Q E okay, I will just maybe write a little more elaborate steps. I have e power A transpose T Q e power A T, the transpose of this. So, this will be 0 to infinity, the transpose of e power A T Q transpose e power A transpose T, the transpose of it. Okay. So, the first term would be e power A transpose T. Q is symmetric. Symmetric is what? Q equal to Q transpose. So, I just write it as Q, and the third term will be e power A T dt, and P transpose therefore is equal to P. Okay. Now, this is done. Next is say 3.1, is P a positive definite matrix? What is the definition of a positive definite matrix? That X transpose P x should be greater than 0 for all x. Okay. I do not really do an eigen value test here, but I just do by definitions. Okay. Just take an arbitrary vector z in Rn, okay, and then compute this quantity z transpose P z, that is 0 to infinity z transpose e power A transpose T, which is again the definition of P, e power A T times z times dt. Now, this is some vector, right, we will call it W, and then this therefore will be W transpose. Okay. I have 0 to infinity some vector W transpose, this is again depending on time, Q W T. Okay. Now, what do I know? I know that Q is greater than 0, and therefore, if Q is greater than 0, then this quantity should be greater than 0. Okay. And therefore, I have that Z transpose P z is actually greater than 0, given that Q is also positive definite, and then I just invoke the definition, right. So, if I have a vector transpose Q times the same vector, that should be greater than 0, and this will hold for all Z. So, I am not defining any particular Z here, but this will hold for all Z. So, whenever okay, Z transpose P z being equal to 0, this would imply that this thing is 0, W transpose Q of W is 0. Okay. Now, when can this happen? This can happen if W t is 0, right, from the definition of the positive definite matrix, that this will be 0. So what was the definition? If we recall, we go back. Right here. So anywhere apart from the origin, it is greater than 0. So at when x equal to 0, it is obviously equal to 0. Okay, which means that this should be 0, that is e power at times z is equal to 0. And I know because A is exponentially stable matrix, that this guy will not be 0. So the only option left is z equal to 0. Okay, and therefore we have proven that P is not only symmetric, but is also positive definite, right. So we are done now with these properties that in the step. So I just verified that the integral is finite. Not only that, I also showed that P solves equation 2, right, which was essentially this equation. Third step, I proved that P is symmetric and it is also positive definite. Last one is to show that this P is actually unique, that you cannot have some other P1 or P2 or P prime which solves this equation. Okay, so how do we go about proving this? And much of proofs sometimes are also by contradiction. So I assume or I begin with assuming that let there be some other matrix P1 which also solves this, and see what happens. If there is any other candidate solution, let me compare that with my original solution and see does there actually exist another candidate solution to this. That is what how we will prove that P is unique. Okay. Now let me just consider any other P tilde which also solves this thing A transpose P tilde plus P tilde A is minus Q, right. What I already know from the first 3 points here, that P is also a solution. Okay. So this guy P tilde comes from nowhere and claims that okay, I am also a solution. Now I will just verify what does this mean. So I just do some manipulations here. So this is will turn out to be A transpose P. Okay, just write it a little. Okay, A transpose P minus P tilde plus P P minus P tilde A is 0, just by subtracting these equations. Okay, so let me just do a little trick here. I just multiply this on the left by e power A transpose t, on the right by e power A t. Similarly here, so I multiply to the left by e power A transpose t, on the right by e power A t. This will still be 0, the right hand side will not change. Okay. So this turns out the quantity inside that d over dt of e power A transpose t P minus this P tilde e power A t, right, which is essentially what is above, and that actually is equal to 0. D by dt of this entire quantity expands to this big expression here. And what do I know of this expression? That this actually is 0. Okay, when d by dt of something is 0, I know that e power A t P minus P tilde e power A t is some constant. Okay. Now if I show that this constant is 0, then things will be easier for me, because if this goes to 0, if e power A t P minus P tilde, so this is P transpose here, e power A transpose e power A t is 0, then P will actually be turn out to be P tilde, that the other guy who comes and claims to be the solution is actually the solution itself. That is because e power at is always invertible, right. Okay, now how do I show this, that this is actually 0? Okay, look at this this expression carefully, right. This is actually a constant. So, if I were to just plot this with time, so this function of whatever this is, right. So, e power a blah blah blah. So, this is constant. Okay. So, if this is constant, whatever value it holds for t equal to 0 should hold for say t equal to 10 to t equal to 100 and all the way to as t tends to infinity. Okay. So, if this holds at infinity, what happens to this quantity at infinity? E power a transpose t p minus p tilde e power a t. What is the value of this as t goes to infinity? Because e is exponential, because a is exponentially stable, that is what I am been exploiting all the while. So, this will be 0, right, because at infinity I know it is 0. So, it should, if it is constant valued function, then the same value should also hold at t equal to 0, same value should also hold at t equal to 10 and so on. And therefore, this number by itself E or this matrix by itself p minus p tilde e power a t is 0, again because the system is exponentially stable. I started with that assumption, let the system be exponentially stable, and then I proved the condition number 4. Right. Now, this is 0, if this is 0, then I know that p is equal to p tilde, and therefore, p is not only the solution, it is also the unique solution, in addition to it satisfying the property of it being symmetric and positive definite. Okay. So, that was about the proof of this. Okay. Now, what should I prove last? So, that stability or asymptotic or exponential stability is also equivalent to this statement, that there exists again a p for which the following matrix inequality holds, that A transpose p plus p a is strictly less than 0. Okay. So, what are the proof steps? It's a little, might look a little tricky with these steps, but we will do that one by one. So, again define, we will show that whenever this holds, that whenever this expression holds, that this will imply exponential stability. Okay. So, we will assume this to be true. Okay. So, I start by defining a p which is again symmetric, positive, definite, for which 3 holds, right, this one, and I define this quantity like this. This comes from say some equation number 2. Okay. Now, I define another quantity, a scalar signal, right. So, x comes from Rn. So, this will be a scalar signal that the if I show that if v of x t converges exponentially fast, the solution therefore, x of t, the norm of x of t will converge exponentially fast, and this will also mean that the solution of our original system converges exponentially fast, resulting in exponential stability. Okay, we will write that down one by one and then check for ourselves. Okay. So, the idea is that I should show that if this is less than 0, then the system is exponentially stable, or the solution x of t converges exponentially fast. Okay. So, let us say assume that q is such that A transpose p plus p a, that this is now greater than 0. Okay. So, if a condition like this is holds, then this will be obvious. Okay. Now, define a function v of t is x transpose t p x of t. I will slowly tell you what is the physical significance of this function, but for the moment we will stick to the proof of what we are supposed to do here, proof of exponential stability. Now I take the time derivative along the system trajectories. So this will be I am computing x transpose t p x plus x transpose t p x dot of t. Okay. Now what is x dot? X dot is always a x. Okay. So what I get here is this will be x transpose a transpose p plus p a x. What is this? Minus x transpose q x, and this is less than or equal to 0. Okay. So this is what I have now. Okay. Now just look at this v dot. Okay, it's a function, right? So v dot. So v is a real valued function, and if v dot. Okay, what is v dot is now less than or equal to 0. Okay. So what does this mean? This means that v dot or v of t is a non-increasing signal, and if v dot is non-increasing, then v of t, just say I take any arbitrary time t p x of t would be less than or equal to the value of the signal v at 0 is x transpose 0 p x of 0, and this holds for all t greater than or equal to 0. So what does this mean? That v is a non-increasing function. So v can either it may be constant or it might decrease or whatever, right. So the value at any time, so if this is t equal to 0, so the value of v at t equal to 0 will always be greater than the value at some other time t, or the value of v at some time t will be either less than or equal to its value at t equal to 0. Okay. How did we prove this? We proved this by just taking the derivative of v along the system trajectories and assuming we know that this is true. So the idea here is to show that satisfaction of this kind of a matrix inequality leads us to exponential stability. Okay, next. So v is x transpose p x. Now this x transpose p x from the matrix properties which we listed earlier in this lecture is greater than equal to lambda min, the minimum eigenvalue of p times x square. Okay. So from this what I can conclude? First I can conclude that x of t square is less than or equal to x transpose p x, okay, over lambda min of p. Okay, what is x transpose p x? X transpose p x is the function which I defined earlier, v of t. This remains the same. Okay, this is less than or equal to v of 0 because v is a non-increasing function as proved just in the previous steps. Okay, and this is valid now for all times t greater than or equal to 0. Okay, so what does this mean? If I just take these two expressions, v of 0 lambda min of p, Okay. So, this is known to me, the value of the function at 0, p is also known to me, right, because I assume that there exists a p which satisfies this inequality. Now, what does this tell me about the solution? It tells me that the solution is uniformly bounded. Sorry, that whatever happens, the solutions will now, maybe they start here, they go here, and whatever, they will always be bounded by this number here, this guy, V0 by lambda min of p. So, this is uniformly bounded, and therefore, I can at least now with this step say that the system is stable, marginally stable, so to speak. Okay. Now, next step to show is this also asymptotically stable, asymptotically or exponentially stable. Okay. Now, let's do this thing. Okay. Now, this matrix Q, which was here, this guy, here and so on, this matrix Q is also such that x transpose q x will be greater than or equal to lambda min of the same q x square. V, sorry, this V of t, which is x transpose p x, the value of this is always upper bounded by this lambda max of p times x square. Okay. Now, look at the expressions for V dot, right, starting from here. What we can say is the following, that V dot, which is minus x transpose q of x, this will be less than or equal to the negative again of lambda min of q x square. Okay. This will be less than or equal to, so I just used on top of that this inequality, minus lambda min of q over lambda max of p times v, and this happens for all times t greater than or equal to 0. So, just a little steps which you can easily verify from all the expressions that we have written here. Okay. So, let me call this, so this is again, this will be a number, right. So, the minimum eigenvalue of q which is known, and the lambda the maximum eigenvalue p of p which is known. So, this will, let me call this as mu. So, I have V dot is less than or equal to some number mu again with V of t, right. So, this and this. Okay. Now, I have a differential equation now in V which looks something like this, V dot of t is less than or equal to V of t. Now, there was this thing called the comparison lemma which I stated, that whenever V, which is a differentiable function, I know that my V there over there was a differentiable function, is less than or equal to mu. Mu was the ratio of those minimum and maximum eigenvalues of q and p respectively with a negative sign. Whenever this happens, then V satisfies something like this. Okay. So, let us exploit that and write down. So, with applying the comparison lemma now, okay, what do I have now? What can I say about V? This V of t is now less than or equal to e power minus, so e power minus of, I will call this lambda, let me just say that this mu is actually minus lambda of t. Let us say for simplicity t naught is the is just 0 V of 0 for all times t greater than or equal to 0. So, this lambda is lambda min of q over lambda max of p. Okay. So, what does this tell me about V? So, V is a function, this lambda will always be greater than 0 because q and p are positive definite matrices. So, all their eigenvalues will be strictly positive. This negative sign will add up to that and say that this V of t as t goes to infinity, okay, will go to V of 0, right. Okay. Now, okay, V of 0 could possibly be the origin also. So, this, and at what rate does it do? This quantity here tells me now that V of t converges to 0 exponentially fast, right. Okay. Now, if V of t converges to 0 exponentially fast, how are V and x related? V and x are related via this. So, if V goes to 0 exponentially fast, then x of t will also converge to 0 exponentially fast. Okay. What is the relation between x and V? So, from here I can just say this, if I just restrict till here, I have that x of t is less than or equal to V of t over lambda min of p. Okay. V converges exponentially fast and therefore, x converges exponentially fast, and therefore, okay, where did we start with? We started by assuming this to be true, and if this is true, this now implies that x converges exponentially fast, or I have proved exponential stability of x dot equal to a x, right. So, those were a little proofs of how all these statements were equivalent. So, we just invoked a few properties of the matrices that we started off with today. We invoked the comparison lemma. We also invoked the relation between the definitions of positive definite matrices and their relations with the minimum and the maximum eigenvalues. These proofs are nice and very intuitive also. It will be nice for you to just write down the steps for yourself, so that you get an idea of how proofs in general are done in any control literature. So, that might be easier for you then to understand any other research papers in this area. Okay. So, just to conclude, what we did today was we started off with proving lots of Lypaunov stability proofs, started off with giving eigenvalue conditions for asymptotic stability, and then we had some kind of an matrix inequality like conditions to prove stability. Next lecture will be a little short. I will skip all those proofs because the steps will be exactly the same as what we did in this lecture. So, we will extensively deal with discrete time systems in the next lecture, and that is coming up shortly. Thanks for listening.